Many people are asking us why FE Core hasn't done anything yet. The answer is that we have been working on this first experiment before even announcing FE Core.
FE Core.
We never stopped. The first experiment was planned to be done when the lake is completely frozen, but it never froze, so we decided to do it whether it freezes or not, and it will be done very soon.
So, what is the first experiment?
The first experiment will be across Lake Balaton in Hungary. We will try to aim the laser across the lake at the lowest possible altitude to see if it will hit the other side of the lake 65 kilometers away. If it doesn't, then we will see if we can see the source of the beam from the lowest possible altitude. The date of the experiment is still unknown because it depends on the weather, but most likely it will be done in February 2018. We are still hoping the lake will freeze, even if only a thin layer with sub-zero temperatures, because this will reduce or limit the effects of refraction to a bare minimum.
What are you going to do if the lake doesn't freeze this year?
We will try to do it from land to land without having to use a boat. Dr. Zack and Sander have already gone to the lake to investigate how we are going to do it, and they said that doing it from land to land also works, since they have already seen the laser perfectly from 21 to 23 kilometers in Pretest.
Oh, yep. That's right.
Look at it. Look at the beam. That's the beam, man.
Yep.
Look at it.
They could not measure the exact height of the beam because aiming the beam to where they were standing was not possible. Moving the laser horizontally by as little as 1 degree means that the laser beam will move 366 meters in 21 kilometers, which makes it nearly impossible to aim the beam to the point you want, not to mention that you cannot see your target at all. The team at the target location will have remote control access of the laser so that it can be positioned to target their location. Many people think it's an easy task, but it really relies on very precise and small movements. You only know how complicated it is when you try to do it yourself.
So what are you going to do in this case? How are you going to solve this problem?
We have already built a mount that will make our job much easier. It will be controlled remotely for ease of positioning by the team at the target location. The mount is so precise that it moves 0.00000247 degrees per step. This means that at 60 kilometers, the laser will move about 2.6 millimeters.
What are the specifications of the mount? How was it made?
The custom-built mount contains 2 stepper motors, 1 power supply, 1 control interface with remote control, and is made out of aluminum for ease of transportation. This is the first image of the mount before all options were installed.
Who designed and built the mount?
The mount was designed and built by Mike Cavanaugh. The idea is simple, but designing it and making it happen is quite difficult. Remember, 1 step is 0.00002478 degrees. This is a lot of precision. Now the mount is almost ready, and all we need to do is wait for the right time to go to the lake to perform the test.
How does it work?
The mount moves horizontally and vertically. We can automate it to make any movement we need.
How long is it going to take to get all the measurements?
It really depends on many things such as the weather, so we will spend around 7 days in Budapest, but the experiment can be done in 2 days or 3 if everything goes as expected. We also want to spend more time to measure refraction to see how it affects the light at long distances.
Would this break the world record?
If everything goes as we expect, this experiment will actually set the world record for the longest distance laser targeting in history and be verified by a third party, unlike the moon distance laser targeting done by NASA.
How can you see the laser beam from the other side of the lake if the Earth is curved?
If the Earth is curved, then we will not see it at all. Bear in mind that the curvature at such long distances should be very noticeable. Let us give you an example so you can understand this. If the laser's elevation is 20 feet or 6 meters, and the distance to the target is 40 miles or 64 kilometers, then even if the laser is tangent to the water surface, it will still be 794 feet or 239 meters above our heads, and it may be impossible for us to reach it.
What happens if you see it?
Then we will take all the measurements necessary to see why it didn't confirm with the Earth's curvature, and we will share these results with everyone. We see it or not. The results will be shared in either case. Our next experiment will be on the ocean to see how that compares with the data from the lake test.
Will you account for refraction over the lake?
We are trying to find a way to measure refraction on the lake and see how and if it will bend the light. Will it bend the light upwards or downwards? We also want to see the difference in refractive effects between day and night. Refraction should not be the same throughout a 24-hour period. This is one of the reasons why our team will spend 7 days to study as many aspects of the test as time and weather permits.
How will the laser be leveled?
Leveling the laser is not an easy thing to do. Many people think that using a spirit level is enough to level it, but a spirit level can never level it precisely, not over those distances. This is not a picture you want to hang on a wall. This is a line that will be more than 60 kilometers long. The best way to do this is to put it as level as possible with a spirit level or any other tool, and then shoot the laser to a short distance, like 10 or 15 kilometers away, and then do a longer distance until we reach the longest distance possible. You can say that the entire experiment will be done to level the laser through a long distance. If we aim the laser directly to the target, which is over 65 kilometers, then we may never find the laser to measure its height. The distance is just too long, and it's nearly impossible to find the target. So this is why we will try to walk the laser to the endpoint a few kilometers at a time. We have already done this in the pretest to test this method.
How much divergence will the beam have?
Well, the divergence is going to be 0.08 millirad, so we estimate that in 65 kilometers, the diameter of the laser beam will be around 5.3 meters.
Is the laser strong enough to reach the end of the lake?
This is something that we will test. The laser experts said that it is designed to reach longer distances, such as 100 kilometers. But of course, to confirm this, we will have to do the experiments. Such experiments at these distances have never been done before, so this is going to tell us a lot of things. The laser beam is not the only problem we have. The weather is the worst problem. If the weather is foggy, like in the pretest, then we may not be able to do anything.
What would happen if the laser beam didn't reach the target?
If the laser beam doesn't reach 65 kilometers, then we will go back to 21 kilometers as it was confirmed to be seen from that distance in the pretest. The divergence of the beam at that distance was estimated to be 1.5 meters. They didn't measure it because it was a bit far away and hard for them to point it to the target, but they could see it was around 1.5 meters in diameter, and if we do the math using 0.08 millirads, then the beam should have been around 1.7 meters in diameter. So their estimation was pretty accurate. So if the weather is clear and the laser is powerful enough to reach 65 kilometers, then the result will be as we expected.
How high was the laser when they could see it from 21 kilometers or 13.04 miles?
It was about 1.5 meters, or about 5 feet above the water surface.
How could they be able to see it from that distance?
If we do the math, the target should have been hidden behind 21.6 meters, or 71 feet of curvature, because the distance is 21 kilometers and the height of the laser is not more than 1.5 meters. Even if we say that the laser was 2 meters high, then the target would still be hidden behind 19 meters of curvature. And 19 meters is like a 5-story building. You have to be on top of this building to be able to see the source of the light, yet it was completely visible from their height. And they were standing on the shore around 0.5 meters or 1.64 feet above the water surface. And the tallest of them was 1.86 meters or 6.1 feet. So if we do the math from their side, 0.5 meters plus 1.86 meters equals 2.36 meters, or 7.74 feet. Then the source of the beam should have been hidden behind 18.8 meters, or 61.9 feet. Again, a 5-story building.
Does that mean anything?
Well, right now it just means that the laser was seen from an impossible distance, but we shall wait till the end of the experiment, and then we will come to a conclusion.
Does this pretest that Sandor and Dr. Zack have done prove anything?
It really depends on what you mean by proof. To some people, it may prove something, and to others, it may mean nothing. Some people may think it was faked, as it was not filmed properly. People should know that they went there to test the laser and do other tests as well for the team, but we decided to share their videos to let people know what we are preparing for.
We heard that you are using a collimator lens. So what is the collimator lens, and what does it do?
It has a huge laser resonator and a multiple lens system that makes the laser beam not diverge in a short distance. So as we said before, the divergence is about 0.08 millirad, which makes the beam's diameter at 65 kilometers about 5.3 meters. Without a collimator lens, the beam would be a lot wider and impossible to see at 65 kilometers, or may not even reach that distance. A laser without a collimator lens cannot go that far no matter how powerful it is.
Final question. What is the maximum panning angle of the mount?
That's one of the problems we are facing. The maximum angle is 6.5 degrees and we need about 17 degrees. So for this reason, we decided to move the pan axis to the middle of the mount to create a larger pan angle. That changed the pan resolution from 0.00002478 to 0.0000077.
Some sections of this video were used with permission from the copyright owner. We are not responsible for copyright strikes issued to your channel by the respective owners if you mirror this video.